Yeah, thank you. So I'm giving this presentation on behalf of Tim Nagel, who is postdoc at the CNRM, and it's called Toward Local Climate Zone-Based Track and Mixing Length Parametrization for the Urban Environment. And the results of the study are already published in Boundary Layer Methodology. So if you want to simulate urban areas at high resolution, you know that when the resolution increases, the domain becomes more and more heterogeneous, and at the district scale, in 100-meter resolution, you can use the urban canopy models, and if you want to explicitly resolve the buildings, you have the CFD models or mesoscale models with inverse boundary method. And so the objective of this presentation is actually to use microscale models to derive parameters that can be used to better, to improve the multi-layer urban canopy models, and more precisely the drag coefficient due to the buildings and the urban turbulence mixing lengths. And similar things have already been done, for example, with CFD models for very idealized morphologies, like line or staggered arrays of homogeneous height buildings, and they have used it to derive parameters for the BEP multi-layer urban canopy model. And it has also been done for real urban districts, like some districts in real cities. The only issue with this is that it would not be possible to do it for every real district because the computational cost is just too high. And that's why the idea of this work was to do it for the local climate zones. So we have this classification of typically occurring urban morphologies worldwide. And so the idea is to procedurally generate districts resembling the local climate zones, and then we simulate these at a very high resolution to derive the drag and mixing lengths to then be used in multi-layer urban canopy models. And what you can see is that some of these morphologies actually have relatively similar lambda p and lambda f parameters, even though they don't look the same. And we will see that this causes issues in the following. And just one thing about these districts, they have about 800 times 800 meters with two major roads and a central square, so this might maybe some biased results a bit into one direction. And the simulations are all done for neutral atmospheric conditions, and they are made in a way that we have downscaling of the turbulent energy cascade. So we have a domain at 96-meter resolution with cyclical boundary conditions, so it's actually infinite. And it resolves like the largest eddies of the boundary layer, and then there's a dynamical downscaling to 1 meter resolution. And in a previous study, we actually verified that the turbulence cascade is actually well downscaled. And in the 1 meter domain, the buildings are then resolved using the immersed boundary method. And the parameters that are derived from these microscale simulations are the drag coefficient, which is diagnosed based on the pressure differences before and after the buildings, and the wind velocity, and the parameters like building density as a function of height and frontal area density as a function of height. And the other parameter is the turbulent mixing length, assuming a TKEL closure, which is diagnosed based on the momentum flux and the turbulence kinetic energy, the vertical velocity weight. So first result, so we can look at the velocity and turbulence kinetic energy profiles for the different local climate zones. So this would be like the normalized velocity profile, and they strongly differ because of the very different density of these morphologies. They exhibit an inflection point between a convex profile above the urban canopy layer and a concave profile in the urban canopy layer, with the only exception being the LCZ9, which actually behaves, so sparsely built, which behaves like a rural environment and not like a urban environment. There's no inflection point. The velocity profiles in the urban canopy layer are not exponential, which has already been stated by a previous study. And for the turbulence kinetic energy, it peaks at the height of the highest buildings, or maybe a bit higher for some. And this is also in agreement with some previous literature. And what we can see is that in some cases, so the lambda p, so the plane area and the frontal area density lambda f, are not are giving you different results, even though they are quite similar. For example, this would be like the result for the LCZ6, whereas the LCZ10 is here. So even though they have very similar lambda p or lambda f, you get a different profile. And this is actually an issue because parametrizations will often assuming that you can describe the characteristics based on these parameters. So for the sectional drag coefficient, it's actually relatively close to 0.4, which is the commonly used value in many studies, except for the LCZ, the LZ4 and 1 with the high-rise buildings where it's larger, and it's also increasing towards the surface, and that's why Santiago and Martilli had already proposed the equivalent sectional drag coefficient, which is just one value for the entire canopy layer based on the vertical integral. And they proposed actually a formula as a function of the plane area building density, which we tested, and it doesn't work. So we tested it for the same staggered homogeneous height cube that was used to derive it, and then it works. But not if we do it for the LCZ. So we don't know if this is. So it might show that if there's like a more complex building environment where the buildings are not staggered or aligned, and when there's a variety of building height, then maybe it's just not that easy to describe the parameter as a function of lambda p or lambda f. For the vertical profiles of the mixing lengths, we can find that they basically all follow a similar distribution from an increase from the ground where it's 0 to the middle of the urban canopy layer, and then they decrease towards the top. And this is because the vertical gradient of velocity is strongest there. And then there's another zone above the urban canopy layer. And this is actually something that has also been in agreement with the study by Louis Blanc in 2022. If we look at the dispersive momentum flux, we can see that it is actually, so this would be like the absolute value, and this is dispersive divided by the turbulent momentum flux. So you can see that it's negative for most of the LCZ in the middle and at the top of the urban canopy layer, and positive near the ground. And for the high-rise, it's actually negative everywhere. And if we look at the ratio between the dispersive and the turbulent, you can see that it's relatively small compared to the turbulent momentum flux, except for the mid-rise and high-rise LCZ. And this is some pictures to show the values of this dispersive momentum flux in horizontal and vertical and horizontal cross-section. So it's really negative downstream of the buildings and positive windfall of the buildings. And it strongly depends on how the buildings are organized. You can determine courtyard, or high-rise buildings. And so it is lower than the turbulent momentum flux for most of the local climate zones, but it's not negligible for the mid-rise and high-rise, so it might be included in future parametrizations. We also looked at what is the influence of the large-scale turbulence, which we used a considerable effort to downscale the boundary layer turbulence to this 1 meter resolution domain, and this is basically the same. So for all the different quantities that we have investigated, if you would just use the 1 meter resolution domain alone, so that means that the turbulence is only generated by the buildings themselves. And yeah, unfortunately or fortunately, we get relatively similar results for all quantities. So at least in this neutral stratification case, most of the turbulence inside the building geometries is probably generated by the buildings themselves, and so it wouldn't be that important to take into account larger scale turbulence. So the main conclusions is that we investigated the flow characteristics like velocity, turbulence kinetic energy, drag, mixing length, turbulent dispersive momentum flux for different LCZ morphologies, and we see that the ground-based, so the plane area building density or depth integrated, like the frontal area density parameters, are not suited to describe the flow characteristics for these geometries where there's non-uniform building height and where also the buildings are not staggered. And so we have proposed values of the equivalent drag coefficients by LCZ, but maybe they would also be different if we would change the configuration a bit. That might be something that to be investigated. And we see that the dispersive momentum flux is lower than the turbulent momentum flux for EIZ that are not high-rise. It's not negligible for mid and mid-rise and also for high-rise. And the large-scale turbulence, large scale, and it's like boundary layer turbulence has a negligible influence on the investigated horizontal quantities. And so what we want to do now is that we basically use maps of the local climate zones, because this is something that you can easily obtain for a city of interest or even for an entire continent with recent developments. And so we code these values for the sectional drag coefficient and the urban turbulence mixing length per LCZ, for example, in data sets like EcoClimap. And then we could just attribute them via a lookup table in the mesoscale or regional climate model simulation. But we would also need to look at how robust the things we have done are. For example, if you would take a slightly different configuration with a variety of morphologies within 1 kilometer grid, maybe the results would astonish.
Any questions?
Yeah. Thank you. Actually, I have recently published a paper in boundary layer methodology about the drag. As I found, you just use the pressure drag only to do the modelization, right? Have you considered the viscous drag, except the pressure drag? We know drag has two kinds of types. The first type is the form drag produced by the pressure difference, and the second drag comes from the viscous effect by the friction drag. So have you considered the drag? Because we have the I recently published a paper. I found that being a packing density is very high, as you said, as you saw here, is 0.5. So this kind of building is really high packing density. So the waste in this kind of flow, this kind of geometric, the viscous drag produced by the cubes or by the ground, cannot be ignored. So maybe if you increase this kind of drag, maybe you can improve your results. The first stress. The second one is which kind of software do you use?
Okay, so I didn't do the analysis because I didn't code it, but I'm pretty sure that we neglected the viscous drag and we only took the pressure drag, because we thought that the viscous drag would be negligible, but that might be a problem, as you pointed out. Yeah. And the software we use Python. Well, the simulations are in Meso-NH.
Open form, fluent?
No, Meso-NH with immersed boundary methods.
Okay, I see. So you don't resolve the cubes, but just add the drag. Okay,
no. Yeah. That's a mesoscale model, but it can be run even at 1 centimeter resolution because there's no limitation in the equations, and to represent the buildings, there's immersed boundary method that has been added.
So we need to move on. Maybe any further questions? So we need to move forward. Sorry. I would like to announce our next